I've basically spoken about the transmission lines already. The fact you need to be physically separated by enough distance from a high voltage transmission line to whatever it is that's causing the problem. Yeah? Or causing the short. When we were working in industry, if you've got a 11 kV transmission state, you're fault finding 11 kV, you are basically standing at least 8 metres away looking, unless you are absolutely sure the thing is dead. If you're running at 1.1 kV, 1100 volts, you do not go any closer than 3 metres to the switchboard if you're trying to find a fault, because if you go closer, you might become the earth. Okay, so voltage does throw distances. Voltage is the driving force, it throws distances. The cables, I've got up here cables and skin effect. What we need to worry about, I'm going to magnify an electric cable. We don't transmit current using don't transmit electricity using direct current, because direct current has to happen at whatever the final voltage is needed, which means massive currents, massive heat losses. We'll have a look later on at Westinghouse versus Edison, the two people that drove electricity into New York, and why one was successful and why one wasn't. Basically, somebody tried to sell DC electricity, somebody tried to sell AC electricity. And oddly enough, the person selling DC electricity went bankrupt because of heat losses in the lines. Yeah? So, but when you look at a cable, it's transmitting AC current, positive and negative. That generates, as you know, changing electrical field generates a changing magnetic field. Going back to our generator theory, our motor theory. So, what actually happens on the outside, that is where most of the current travels. Skin effect. If I look at 50 Hertz, domestic frequency, those waves go in from memory 8 millimetres. 8 millimetres. So if you've got a cable that's 16 millimetres round, or a solid bar that's 16 millimetres round of aluminium, that will go into the 8 millimetres in there. So that's 8 millimetres going in that side, that's 8 millimetres going in there. The whole cable is used. I think the skin effect for 50 Hertz is 8 mil, isn't it? Give or take.
Yeah.
Okay. So, does that make sense? As you increase the frequency, obviously the magnetic changes are quicker. It goes less. So if I've got a ship and an aircraft actually run at 400 Hertz. When you're up in the air, the aircraft runs at 400 Hertz, all the electronics, it doesn't run at 50. There, it's a square effect, so I think it's around about 3 mil. Every bit, it's only the outside 3 mil of the cable is carrying current. Yeah? Two reasons why they use cables and not solid bar is, one is those big transmission lines, the cables are that round. If it was solid bar, then you'd basically only be carrying current through the outside 8 millimetres all the way around, skin effect. Yeah? So they use cables because there, skin effect disappears. The other problem, aluminium stretches. Cables are heavy. Heavy cable with something that's low strength is not a good look. They don't use copper on the power lines because copper is very heavy and very expensive. Instead they use something with reasonable conduction, aluminium. So around the outside, they have got aluminium cables. Cross section through a power line. The aluminium cable gives conduction. On the inside, they've got a steel cable, physically for strength. It's sitting on the inside because of skin effect. Make sense? So around the outside, you've got 8mm of aluminium cable, and in the middle you put a steel cable where it doesn't need to carry any electricity. Make sense?